convenience to and the people's likings to join such events, which are short ones in nature, and they are one at a time, one lecture at a time. And of course, this time I'm glad to have Mr. Richard Goodman, who I think in one request agreed to deliver a lecture. We had to only see that the times match. So being in Western country, we had to fix up a time which is 1 hour earlier than our normal time of 6 o'clock or 6 p.m. IST, and more or less suited to him as well, which I think for him it must be about 12:30 now, 1:30 now. No, did I say wrong? 12:30 now, sorry. That is how we are, and we have a strong team back of the house in IIB. Mr. Swapnil Joshi as honorary secretary, Dr. Gopal Rai as another honorary secretary. We have our Director General, Mr. Devate. We have our two strong coordinators, Ruhi Agrawal and Deepika Singh. So, and of course, we have the whole full-fledged executive committee comprising strong-headed professionals. On the lighter side, friends, organization without a strong head is not an effective organization. Your reinforcement will not remain headless in the times to come. I think the way we are seeing the predictions and learning from what has happened in the field of reinforcement couplers, all the reinforcements in future will be headed reinforcement, and it will not be without a head any further. So we will hear what this head is. It may sound very simple, but it will be extremely useful in our practical lives. And the times to come, as it has come in the international other codes, we will also bring it to Indian codes. So let us first hear, understand, appreciate, and then bring it to our Indian practice as much as we can. Thank you so much. Over to Mr. Swapnil Joshi.
Thank you very much, sir, for a quick brief. And let me now go to the introduction of our moderator, Dr. Surya Prakash. He's a professor, civil engineer at IIT Hyderabad. He's a recipient of prestigious Ramanujan Fellowship from the Government of India. Before joining IIT Hyderabad, he has worked as a design engineer at Structural Group Incorporation, Baltimore, USA. He received his PhD from Missouri University of Science and Technology, USA in 2009, obtained his MS degree in structural engineering from IIT Madras in 2005. His research interests include use of advanced composite materials for civil infrastructure, precast systems for affordable housing, and repair and rehabilitation of structures. He has 15 years of research and teaching experience, guided 4 PhD students. More than 65 research papers are being published internationally in reputed journals, and presented more than 50 papers in national and international conferences. He is also serving as an associate editor for ASCE Journal of Bridge Engineering, and a member of ACI, AC, ICI, and STR, and a committee member of IIB as well. So he's a member of IIB. So with this small introduction, may I now hand over the forum to Dr. Surya Prakash to take it forward. Over to you, sir.
Yeah, thank you, Swapnil. I think it's a pleasure to be part of this wonderful event. And I welcome all the esteemed panelists. We have all experienced experts who have joined us today, and looking forward to this fantastic session. Let me now introduce about Dextra. And Dextra is established in 1983 by French expatriate entrepreneurs. Dextra Group has developed over a long history, during which it has encouraged those with an entrepreneurial spirit and constantly strive towards innovation and growth, leading to diversification. And Dextra's main activities are manufacturing, trading, and freight forwarding, all within the construction and industrial sectors. And today, Dextra Group employs over 900 people worldwide, and they have commercial presence in 55 countries through a network of direct subsidiaries and long-term partners. Over the years, Dextra has involved in more than 10,000 major construction and industrial projects worldwide. They also provide unique global experience and expertise, which are continuously spreading throughout with the help of network of their partners. And briefly, they do offer from three major industrial sites located in Bangkok, Guangzhou in China, and Mumbai. They have completely owning their manufacturing facilities and processes, and this is allowing them to have a complete control over the timing of their operations and so on. The major product what they're supplying is for concrete reinforcement and rebar splicing. So, and also today we are going to talk about another important item, that is the headed bars, which is also, as correctly said, it is picking up usage in India as well, and composite FRP rebars as well. I think incidentally that is also Dextra member is going to have a presentation in the next week. So this is just a small introduction about Dextra. Now I request Deepika to play the video about Dextra. Yeah.
So, Deepika, can you stop the video?
Yeah.
Yeah.
Okay, I think, thank you, Deepika. I think now let me introduce our eminent panelists here. And the first panelist is Mr. Umesh Rajashekhe. He is MD of Spectrum Techno Consultants Private Limited. A brief introduction about Mr. Umesh. He has over 30 years of experience in the planning and design of bridges, flyovers, large span steel structures, marine facilities, industrial structures, pre-stressed and reinforced concrete structures, and shell structures. He graduated from a bachelor's from VJTI, one of the famous engineering colleges in Mumbai in the year 1987. And thereafter, he went on to do his master's from IIT Madras in 1991. He is also involved in many prestigious structures, design of many prestigious structures like cable stayed bridges on various rivers like Mahi, Mapusa, Ambura, Bhopal, Patna, Vadodara, various cities, including a number of precast segmental bridges, metro rail viaducts, long span steel truss and arch bridges. And he is also a member of various BIS and IRC committees, and has also published number of papers and national and international conferences and journals. Sir, it's very pleasure to have you here. So, Deepika, you can go to the next slide if you don't mind. Yeah. And again, we have one more eminent panelist, Engineer Alok Bhaumik. He is Managing Director of BSCC and BS Engineering Consultants Private Limited. And he is also the immediate past president of Indian Association of Structural Engineers and Managing Director of B&S Engineering Consultants Private Limited. And he has more than 40 years of design consultancy experience in transportation infrastructure, and he has accreditation of International Professional Engineer from Institution of Engineers India, and he is also fellow of Indian National Academy of Engineering, and he has received several awards in his professional career spanning over 40 years. In 2018, he was awarded SP Joshi Memorial Award for Excellence in Bridge and Structural Engineering. He is an active member of several professional bodies, including IEI, CEAI, IABSC, and IAS Truckee, ECI, and code-making bodies, IRC and BAS. And he is also the chairman and editorial board of quarterly journal Bridge and Structural Engineer published by ING IABSC. So we have an eminent panelist. Sir, I welcome you for this webinar. Looking forward to fruitful interactions with you. And Deepika, can you go to the next slide? Yeah, again, one of the doyens of our bridge engineering community, and I have the pleasure of introducing Dr. Harshavardhan Subbarao. He holds a master's from University of Michigan and PhD from Imperial College, London. He's been involved in a number of landmark projects such as Signature Cable Stayed Bridge in Delhi, 4.6-kilometer rail-cum road bridge in Patna, bridge number 20 on JURL, various metros, viaducts, elevated roads, arch and extra doors bridges, underpasses, etc. And he is also vice president, member of technical committee of International Association for Bridge and Structural Engineering, IABSC Zurich, and chair of its bulletin editorial board, and members of Highway Research Board of India. And he is also serving in various committees of Indian Road Congress, Bureau of Indian Standards, FIB, and various international and national bodies. And he has a very rich experience, more than 35 years, and he has authored number of papers and bridge project to his credit. Sir, it's a pleasure to have you as part of this webinar. Looking forward again to your valuable comments as we go along with the event. And we have one more panelist. I'm not sure Engineer Mahendrakar has joined, but anyway, let me introduce. Maybe he may be joining a little late. And Engineer Avinash Mahendrakar is known personality in the field of bridge engineering. He is a highly qualified and experienced professional bridge engineer with sustained experience in private sector with both contractors and consultants. And he has specialization in planning, designing, and supervision of construction of various types of concrete bridges, from small to long span bridges. And he is currently designated as General Manager of L&T Transportation Infrastructure, and he is heading the Structures Design Department. Sir, welcome you as part of this webinar. And okay, let me finally go and formally introduce our speaker, Engineer Richard Goodman, and Technical Manager of Dextra. And first of all, thank you for having agreed to deliver this webinar. And he's currently based in the UK with a degree in civil engineering. Richard has worked for civil engineering contractors, steel mills, and manufacturers of construction products. And he has over 25 years of experience in the design of steel products for construction. And he is a specialist in the design, manufacture, and use of such steel products. And he's also currently the technical manager for Dextra, and having held the position for the past 7 years. I think it's very nice to have you here today, Mr. Goodman. And now let me leave the virtual floor to you. You can start the presentation. I think I request all the panelists to, if you can help me with answering some of the comments, the very important comments, probably we can take it at the end of the session once the.
Hello, thank you. Can everybody hear me?
Yes, we can hear you very well, Mr. Goodman. Yeah.
Fantastic, thank you. Thank you very much for the introduction, gentlemen, and it's a pleasure to be with you here today. Thank you for inviting me. So let me see if I can forward this. Okay, so today's webinar will be about headed reinforcement anchors, and in particular how you can design with headed reinforcement anchors, or typically called headed bars, in accordance with Eurocode 2. So headed bars then are used as an alternative to either a straight length of rebar, which is bonded, or a bonded bent length of rebar for anchoring reinforcement. So I'm just going to give a very quick company overview, tell you who we are and what we do. You've seen the video already. Before looking at the benefits of using headed bars and what their various applications are, a quick look also at the various headed bar systems that Dextra manufacture, before looking at how you can design with headed bars in accordance with Eurocode 2, which would set out the parameters of design, including the spacing requirements, the edge distance, etc. But what if you can't meet those spacing requirements? What can you do? Some comparisons with other codes of practice around the world, a look at other products and technologies, and what other guidance and support is in the marketplace, and what guidance and support can Dextra offer. So you've heard a little bit about Dextra, so I won't dwell on this too long. So we were founded in 1983 by a group of French entrepreneurs. Our head office and main manufacturing facilities are in Bangkok, in Thailand. We've got over 900 employees in 13 offices around the world and active in 55 countries. So, oops, let me go back one. So as well as having a factory in Thailand, we do, of course, also have one in India, just outside Mumbai, and we have a factory in China where we design and manufacture our ground engineering products. Generally around the world, we work through distributors, and with headed bars, in fact, the processing of the end of the bar is performed with machinery which is designed and manufactured by Dextra. So in India, this machinery will be either at our factory or on site, or possibly with cut and bend rebar suppliers. So as well as rebar couplers and headed bar systems, we also have a range of engineered bar systems. So steel bar systems for post-tensioning or pre-stressing of concrete, steel bar systems for tying marine walls, and architectural or structural steel bar systems. And we have a range of ground engineering solutions, some of which make use of our steel bars. Others make use of fiber reinforced polymer bars, which we manufacture at a factory in China. As a company, we have a commitment to quality. So as a company, we have quality assurance through Bureau Veritas, through UK CARES, that is the Certification Authority for Reinforcing Steels, and also through the American Society of Mechanical Engineers. We also have an in-house third-party accredited test laboratory where we're able to test steels that come in for further processing, and we're able to continuously test our products. Our products are certified by various bodies around the world, and these bodies tend to audit us twice a year and independently test our products continuously. So what then are the benefits of using headed bars and the various applications? Well, as I said, headed bars are used as an alternative to either a straight length or a bent length of bonded rebar which is bonded to the concrete to form an anchorage. So Eurocode 2 gives a number of different methods of anchoring reinforcement, but the most common method is just to provide a 90-degree hook, and it gives information about what it calls a basic tension anchorage and an equivalent tension anchorage. So everything from this dotted line, which you can see, and all of this bent bar from the dotted line is used for the anchorage in the anchorage zone. It's used to anchor the reinforcement. So on the right-hand side then is the equivalent headed bar, provided the head is large enough and the concrete is strong enough. So the full design capacity could potentially be taken by the head and be transferred through the concrete. However, it is common though not to use in this configuration, but rather to use the head at the far side of the adjoining member or the far side of the member where you're anchoring the reinforcement. So relative to the bent bar, where you can see my cursor, it would generally be in this location. So there is potential for a saving on the amount of reinforcement that gets used. And of course, you're not or don't have to bend the reinforcement. But in fact, the two main advantages of using headed bars are firstly that it has the advantage of reducing the reinforcement congestion considerably. And secondly, of course, handling and fixing a straight bar with a head on the end is a lot easier and can be a lot quicker on site than fixing a bar which is bent on both ends. So of course, this can lead to a time saving on site, and a time saving can lead to a cost reduction for the contractor. So I'm now just going to show some typical applications for headed bars. Firstly, beam column connections. This is a very typical application. So the bars go all the way through the adjoining member, and they're terminated with the head on the very far side of the member. The top of columns or top column crossheads, again, as an alternative to a bent bar anchorage. They can be used at the top of pile caps or at the end of cantilever members or in corbels. They can be used for punching shear reinforcement or in fact any transverse reinforcement application. So here you can see the head is just on one end, on the lower end of the reinforcement, and these bars can then be dropped down into position. So it's very convenient to do this for transverse shear reinforcement, particularly if you have a very thick raft or slab. And finally, they can be used as cross-wall shear ties with a head on either one or both ends of the tie. So Dextra manufacture a range of headed bar systems, not all of which we sell in all markets around the world, but the heads we sell are suitable for 10 right up to 50 millimeters rebar diameter, and we sell them in two main sizes. So the smaller size, you can see, has a bearing area, that is the bearing area underneath the head that bears onto the concrete, of just over 4 times the cross-sectional area of the bar. And we have this side because it is a prescriptive requirement for the USA Code of Practice ACI 318 for designing with headed bars. We also though have a larger head with a bearing area equal to or greater than 9 times the cross-sectional area of the bar. And in fact, we're finding that the larger head is more commonly used in Europe or where Eurocode is the applicable code of practice. So the 3 systems that you can see in front of you are actually, well, they use the same technology as our rebar coupler systems, but I'm just going to focus on the middle system, our Bartek system, because this is the system we tend to sell in India for our rebar couplers. So the Bartek system, you may be able to see there that the end of the bar is first cut, so it's cut straight, and it is cold forged. It's cold forged to increase the diameter of the bar locally, just at the end, before threading. And then we then simply screw on the heads, either a large or a small head. So by doing this, we don't reduce the cross-sectional area of the bar at all, and we produce a full strength headed bar system, what we call a bar brake system. So ultimately, if this system is loaded to destruction, it is the rebar that fails away from the influence of the head and the headed connection. Not all headed bar systems have this level of performance. The majority don't. So what's the advantages of having a bar brake system? Well, firstly, you have greater factors of safety, of course, on strength. And secondly, you are able to take the joining bar right up to its ultimate tensile strength. And only by taking it up to its ultimate tensile strength can you mobilize the full ductility, the uniform plastic elongation or ductility of that reinforcement. So by having a full strength system, we can make use of the full ductility of the reinforcement. If you don't have a full strength bar brake headed bar system, it means that you're going to effectively end up reducing the ductility of the rebar that the head is connected to, because you won't be able to take it to its full ultimate tensile load. The other systems, GripTech and RollTech, we sell in other regions, so I'm not going to dwell too much on those systems. We've also tried to innovate in this region over the last few years. So this is a system now we have introduced into some markets around the world. It's a system we're calling a pressed connection system. So it has been specifically designed for smaller rebar diameters, 10 to 20 millimeters, and it's been designed so that you can cut and bend the rebar on an automatic cut and bending machine, place that bent rebar onto our machine then, which is fully automated. The machine will heat the end of the bar by an induction heating process. This end head then gets placed over the end of the bar, all completely automated, and then the bar end gets forged to make the connection. At the moment, it's only available with the large size, but potentially the same technology could be used for our small size of head. So this is ideal for use with transverse shear reinforcement, because with transverse shear reinforcement, rather than using what they usually call manual benders, it gets automatically bent in a cut and bend machine. So it can be bent automatically, it can be put on our machine, everything is completely automated, it goes around onto a cooling bed and then gets taken off the machine. So ideal for applications like this. So this is transverse shear reinforcement used on this very thick raft in the UK. And you can see at the top, we have a bent anchorage. So you can see all the anchorages at the top of this raft. And at the very bottom, some 3 meters or so away from the head, you can, away from the bend, you can see the head at the very bottom. So all that happens on this project is they go along and they drop this reinforcement into position and they are tying the top. So perhaps you can imagine the difficulty that they would have if they had a bent anchorage at both ends. It would be considerably difficult and a logistical nightmare to try and construct the reinforcement. So, of course, we hold test reports and certification for our headed bar systems. So we have certification through ICCES in the United States and certification for various systems through the UK CARES, that's the UK certification body for reinforcing steel. And we also have independent laboratory test reports to show compliance with the ISO standard for some of our headed bar products, ISO 15698. So how would you design then headed bars to Eurocode 2? Well, firstly, of course, there are a number of product standards for headed bars, one of which I've already mentioned, ISO 15698, and there's a CARES testing requirement. There's also an ASTM standard, which they use in the United States. But of course, these standards tend to give measures for testing and for the requirements for the strength and robustness of a headed bar system. But what they don't do, of course, is tell you how to design with a headed bar system. So for that, we look to the relevant code of practice, whatever that might be. So in some parts of the world, like in North America, like Australia and Japan, the use of headed bars is prevalent. They use a lot of headed bars. And that's because their codes of practice give information about how to design with headed bars. But the applicable code of practice in Europe, Eurocode 2, and for those countries that use Eurocode 2, in fact, there's no specific information in Eurocode 2 that tells you how to design with headed bars, which has led to a situation where there's not been a huge market to date for use of headed bars. Their use hasn't been great. So with this in mind, we have we contacted Arup, the consultant engineers, and we commissioned Arup to write a design guide for how you can design with headed bars in accordance with Eurocode 2. So rather than being a product guide, this is really a design guide. It's intended as a non-contradictory supplement to Eurocode 2, and it focuses on the capacity of the concrete to resist the forces exerted by the head or by the rebar. So now we're hoping that this will give consultant engineers the confidence to design in accordance with Eurocode 2 and use headed bars. So while Eurocode 2 doesn't give any explicit information about how to design with headed bars, it does give information about large diameter bars. It says that for large diameter bars, which it classifies as 32 and 40 millimeters, splitting forces are higher and dowel action is greater with the use of large diameter bars. Such bars should be anchored with mechanical devices. As an alternative, they may be anchored as straight bars, but links should be provided as confining reinforcement. So for 40 and 50 millimeter diameter bars, it gives you the option of having a straight length of bar as an anchorage or a mechanical device or headed bar system, but it doesn't actually give you the option of a bent bar. Also, I'd like to maybe at this point highlight in the Indian standard IS 456, which is for plain and reinforced concrete, and the design guide SP34, which is the handbook for concrete reinforcement and detailing. It states with regards to the requirements for anchorage, it says that any mechanical or other device capable of developing the strength of the bar without damage to concrete may be used as anchorage with the approval of the engineer in charge. So the guide then is derived from the fundamental principles of Eurocode 2. And for the head strength or the head capacity, we're really looking at the ability of the concrete underneath the head to resist the loads. So the basic requirements for this are taken from section 6.7, which deals with partially loaded areas. That is small areas which are heavily loaded, so it causes local crushing underneath the localized area and transverse tension forces, much in the same way as a post-tensioning anchorage performs. So most of the other expressions are then derived from this or derived from the other requirements of Eurocode 2. So if you have a headed bar and it's embedded in concrete, because the head is relatively small, but the load is relatively high, we get a zone or a volume of concrete directly underneath the head, which becomes overloaded in compression. That is to say, the stress within the concrete within this zone, which is shaded in blue, exceeds the design compressive strength of the concrete, but just locally. So the stress in the concrete is at its greatest directly underneath the head, but at distance it then dissipates. So at dimension h, the stress in the concrete equals the design compressive resistance of the concrete. So as I said, exactly the same really as the kind of thing that's happening with the concrete with a post-tensioned anchorage. Because of this dissipation of force underneath the head, you also get a transverse bursting force. So while the concrete is in compression directly underneath the head, transversely it is actually in tension. There's a small tension force which causes the bursting. So these bursting forces then need to be resisted by having enough concrete around the head or having transverse confinement reinforcement. So if the head is large enough and the concrete is strong enough, in fact, the full design load of the reinforcement can be taken via the head and the load transferred to the concrete through this mechanism by head bearing alone. However, if you have a relatively small head, or if you have relatively weak concrete, you need to take your design force from your reinforcement via a combination of head bearing and rebar bond. And where you're considering rebar bond, the bond length that you calculate needs to be outside of this zone, which is overstressed, essentially because we have these transverse bursting forces within this zone, and therefore a reduction in the bond just locally underneath the head. So the Arup guide then is based on the fundamental principles of Eurocode 2. So for any given concrete strength and rebar diameter and rebar strength, the guide allows you to first calculate what size of head is required in order to take the full load via head bearing alone. It also allows you to calculate the geometry of this overstressed region, so the height h and diameter cb. If the head isn't large enough, it allows you also to calculate the bursting forces, the transverse bursting forces. And once you know the bursting forces, it allows you to calculate the transverse confinement reinforcement that's required to resist those bursting forces. And if the head isn't large enough or the concrete is fairly weak, it allows you to calculate what load can be taken via the head bearing and what load needs to be taken via rebar bond. So knowing then the geometry of this region which is overstressed actually allows us to calculate the spacing requirements for the heads, because these zones of overstressed concrete need to be kept separate. So in the case that you see before you, the minimum center to center distance would be diameter CB. So from here, center to center would be diameter CB, because that is the diameter at the base of these overstressed cones of concrete. And the minimum edge distance to the edge of your concrete would be half of CB. So if your head is too close to the edge of concrete, of course, there can be a punching shear cone failure where the bar and the head tries to punch completely out of the concrete. And one situation which can be prone to this kind of punching shear cone failure is in a beam column connection, because effectively you can get a zone of concrete where there's effectively not enough concrete to resist the forces from the head, and so you can get the propagation of a punching shear cone failure. However, this failure mechanism can be calculated in accordance with Eurocode 2, and if necessary, additional reinforcement can be added to prevent this failure mechanism occurring. So Eurocode 2 does allow you to use headed bars. It calls them mechanical anchorages. That's taken to be meaning headed bars. And it gives information about large diameter bars. It says that large diameter bars need to be anchored with headed bars or with straight lengths of anchored bar. But it doesn't explicitly tell you or give you any design information. And it doesn't explicitly tell you that you can take part of the load via head bearing and part via rebar bond. So where does the justification for doing that come from? Well, there are many reports, technical reports, and many papers that have been written about this based on experimental research. And all of them show that if there is a bonded length in the anchorage zone, load is first taken by this bonded anchorage zone length. But very, very quickly, and at quite small loads, the load is then transferred also to the head. And thereafter, it is taken via head bearing and rebar bond if there is an available bonded length. And of course, if there isn't an available length, bonded length in the anchorage zone, then it means the load has to be taken via the head alone. Also, Eurocode 2 was developed from the FIB Model Code 1990, and therefore it's anticipated that the next version of Eurocode 2 will rely heavily on the latest version of the FIB Model Code, the 2010 version. And that indeed gives information about how to design with headed bars. And it gives information about how to design under two conditions. One where you're taking the full load via head bearing, and one where you're taking the load via head bearing and rebar bond, Also, the American Code of Practice, ACI 318, which is the provisions of which for headed bars are entirely drawn from experimental research. Head, you need transferred into the concrete through a combination of bearing force at the head and bond forces along the bar. So directly underneath the head, we have this zone of concrete which is overstressed in compression, but we're also getting these small transverse bursting forces which need to be confined. So generally you would need confinement reinforcement or physically enough concrete around the head to resist those forces. And within the guide, there is the Arup Dextra guide, there is information about the transverse reinforcement that can be used. So it could be in the form of straight bars, as shown in the diagram. It could be closed links or hoops. It needn't necessarily go through this zone which is overstressed, but really just suitably placed to confine it, to confine the concrete. And it needs to be placed between 0.4 H and H, where H is this height of overstressed concrete. So the expressions for the transverse force and the transverse reinforcement that are given in the Arup guide, Arup Dextra guide, relate to the forces in one plane only. So this plane is at right angles to the headed bar. So for example, if you calculate that you require 4 individual bars to resist the transverse resist the transverse bursting force, then it also means that you need 4 bars at right angles to the ones shown in the diagram there. Because the forces or the bursting forces act 360 degrees around the head. So here we have a plan view of 3 heads which are very closely spaced. They are, if you like, an array of heads. So in the center, we have our anchorage. Right in the middle of our bar, this is our head. And the lighter blue zone is this zone of concrete, which is overstressed. So the transverse bursting forces then act 360 degrees around the head, which means that if you have an array of closely spaced heads, the confinement reinforcement only needs to resist the unbalanced forces. And as you can see, the forces between the heads are actually equal and opposite. So they effectively cancel each other out. So which means that longitudinally along the array of heads, you would need reinforcement, which equates to the forces from one anchor only, whereas transversely, you would need reinforcement, which equates to the forces from all 3 anchors in this case. One question which we often get asked is, can headed bars be used in compression for compression reinforcement? And of course, the danger then in using headed reinforcement for compression headed bars for compression reinforcement is that there is potential for a punching shear cone failure if the load is transferred to the head. One way, though, of preventing this happening is to ensure that you have a bond length underneath the head which is capable of resisting the compression force. But it's interesting to note that within Eurocode 2, for bent anchorages, it states that bends and hooks do not contribute to compression anchorages. And it says something very, very similar in other codes of practice also. So in ACI 318, it almost has the exact same wording. So for a bent bar anchorage, that means that you need to take your bonded length as a straight length before the bend in the rebar. So this is the anchorage length for the compression reinforcement. But for a headed bar, of course, the length of anchorage would be the same for the same compression load, but the length starts underneath the head, which often means then that you could have a smaller or shorter anchorage zone because you can start the bonded length of rebar that's required closer to the edge of the concrete. So it even has an advantage in its use if the rebar is in compression. So by using Eurocode 2 as implemented by the Dextra Arup guide, we can set out the minimum spacing requirements and the minimum edge distance based on the zones of concrete which are overstressed and keeping them separate. But what in fact if you can't achieve those spacing requirements? What do you do? Well, firstly, it's important to note that this zone of overstressed concrete and the size of it depends on the concrete strength. So if you were to simply increase concrete strength, you can decrease this H dimension. So the zone of overstressed concrete would firstly be bounded by the dotted blue line, and then if you increase the concrete, it would be bounded by the red dotted line, which means, of course, that you can have closer spacing. But it's not always convenient, of course, just to increase concrete strength. The other thing to note is that generally the equations within the guide assume that you're taking the full design load of the rebar at the head anchorage. So it's being transferred, the full design load is being transferred right at the end of the rebar into the head. So in cases where this isn't the case, of course, you can use a smaller design load, which would make your zone of concrete smaller, zone of overstressed concrete smaller, and allow closer spacing requirements or a closer edge distance. But again, sometimes that isn't always the case. So one technique that can be used, and there are several, but this is perhaps the simplest technique, to overcome the problem if you can't achieve the spacing requirements is as follows. So here you can see two heads which are fairly closely spaced. And if you take the full design load of the rebar, you can see that you are getting zones of concrete which are zones of compressed or overstressed concrete which are bounded by this dotted blue line. So you can see that on plan they overlap, and they overlap the edge distance of the concrete. So what do we do in these situations? What's an effective method for dealing with this? Well, you can firstly look at the geometry of your overstressed zones of concrete and see what geometry is required to fit in with the design parameters. So here then, the geometry is shown in in red. So if we look at the zones then in red, they fit within the design parameters, so they don't overlap the edge of the concrete requirement, and they don't, it means the zones of concrete don't overlap, the zones of overstressed concrete don't overlap between the heads. So once you've assessed and you know the geometry of that concrete, you can see what load is required to be taken by the head to produce effectively that zone of concrete. And then the remainder of the load you can really you can assume gets transferred via rebar anchorage. You need to ensure that there's enough anchorage length within the anchorage zone then to resist the remainder of the load. So here we're taking, instead of the full load via the head, which causes an overlapping of these zones of overstressed concrete with the spacing requirements we need, we assume then that the load, a smaller load, is taken by the head to fit in with the geometrical requirements, and the remainder of the load is taken via rebar bond. So we need to ensure that we have enough anchorage length within the anchorage zone so that there's sufficient bonded length of rebar before the head. And this technique can be used effectively all the way until we get to the very minimum requirements or minimum spacing requirements in order to successfully place and compact our concrete. So these are generally dictated to by the code of practice, in this case Eurocode 2, for the cover, for the maximum and minimum areas of reinforcement in the member, for the spacing between the bars. And then we've given these two additional expressions for A, which is the spacing between the heads, or between the head and the bar, and B, which is this offset dimension. So within the guide, we've given A as the maximum of the head thickness, or 12 millimeters, just again to allow for the successful placement and compaction of the concrete. And we've given B here as the maximum of the head thickness, 20 millimeters, or the aggregate size, and 5 millimeters. So this technique of effectively transferring the load from the head to rebar bond can be used all the way down to get to the minimum spacing requirements required. But as you reduce your spacing requirement between the heads, of course, it means that you need a greater and greater bond length. So how do our heads then fit in with these requirements? Well, if you take a grade 500 rebar and the core parameters within Eurocode 2, so parameters of partial factors of safety and the other factors, if you use one of our large heads, that's a 9A head, you won't need a bond length contribution provided the concrete is C2530 or stronger. And in Europe, this is how we designate it. So the C25 is the cylinder strength, and 30 refers to the cube strength. However, if you use one of our small heads, you need a much stronger concrete, C5060 or 5567, in order to take the full load of the rebar via head alone. But in both cases, of course, you need to comply with the minimum spacing requirements that are calculated. And if you can't, effectively it means that you need to have a bonded length of rebar or an increase in the bond length of rebar below the head. So a comparison with other codes of practice. Firstly, FIB model code does give information, and it gives what I call prescriptive information about headed bars, simplified rules, if you like, rather than working from first principles. And where the load is taken just by the head alone, it gives fairly simple rules for a head with a bearing area of 8A, so slightly smaller than our 9A head. So that means a bearing area just over 8 times the cross-sectional area of the bar. And then it gives the center-to-center distance and edge distance spacing requirements as a function of the bar diameter, all for a minimum concrete strength. But if we were to put numbers to that, it means that for a 32 millimeter bar, we get an edge distance requirement of 112 millimeters. That's from the center of the bar to the edge of the concrete, and a center-to-center distance of 192 millimeters. So how does that then compare with what you would get with the Arup Dextra guide, effectively following Eurocode from first principles? Well, if we were to look at the very minimum strength of concrete, C3037, which is part of these prescriptive rules of FIB model code, in fact, it gives a more conservative result in that we require greater edge distance or center-to-center distance. So we can say that if you were from first principles of Eurocode 2 from the Arup Dextra guide, it's a little bit conservative when you compare it to the FIB model code. But of course, one of the advantages in working from first principles is that you don't need to stick to the minimum strength of concrete, and you find that with increased concrete compressive strengths, the center to center distance and the edge distance start to decrease dramatically. And the same could be said for the actual head size for your headed bar system. So our large heads are 9A rather than this prescriptive 8A head that's given in FIB model code. And if we use a 9A head, such as the Bartek head system, again, we have a reduction in the edge distance and the center to center distance. So there's clear advantages of working from first principles to Eurocode 2 as implemented by the Arab Dextra guide. The American Code of Practice ACI 318 gives a set of simplified prescriptive rules, and they're rules where the load from the bar is taken via a combination of head bearing and rebar bond, and it doesn't give any alternative. And these rules have really been derived purely from experimental research. So the head size needs to be relatively small. It gives it the head size as a 4A head. So this is one of our small sizes, which is really why we chose this small size in the first place, because of these prescriptive rules in ACI 318. And it says that normal weight concrete should be used, and then it gives the center to center and edge distance as multiples of the rebar diameter. And then the thing that changes is the bond or development length, which is a function of the concrete strength, the rebar diameter, the rebar strength, and a number of other factors, depending on whether it's epoxy coated or not, a location factor, a strength factor. So what changes then is not the spacing, but the rebar bond length requirement. But in fact, what is actually happening is, as you have a longer rebar bond length requirement, or as you have a longer rebar bond length, there is less load on the head. Or if you have a shorter load, shorter bond length, you get more load taken via head bearing. And ACI 318 makes reference to ASTM A970 as the applicable product code for headed bars. And ASTM A970 says that a performance class HA head should be used to comply with ACI 318. It also states that the bearing's face shall consist of a single nominally flat surface that lies in a plane perpendicular to the longitudinal axis of the bar. So what other products and technologies are in the marketplace, and perhaps what should you be looking for, and in terms of the product that you should be using? Well, both the working from first principles of to Eurocode 2 and also ACI 318, one of the fundamental requirements is that the head bearing area is flat and it is perpendicular to the longitudinal axis of the bar. So these type of products here, which you can see, and these products are forged from the end of the bar, they shouldn't be used because the heads aren't flat and they're not perpendicular to the rebar. The shape of the head itself actually dictates the volume of concrete underneath the head, which is overstressed. So with a round head, you get this conical volume of concrete, which is overstressed underneath the head. And clearly with a square head, it becomes a pyramid of overstressed concrete. And this matters. And it matters because with round heads, you could rotate this bar and the geometry is all the same. But with other shapes, such as square heads, of course, the geometry of the overstressed region changes. It rotates as the head rotates. So while in theory, you need a center to center distance here of CB minimum, because that's the diameter at the base, or the across flats the across flats dimension at the base of this overstressed concrete. So from center to center would be CB minimum also. But if you were to rotate one or both of these heads, the zones of overstressed concrete would intersect. So to keep those zones separate, you need to increase the center to center distance. But with any shape of heads other than a round head, Then a shape of head other than a round head, this is really, it's impractical to do on site. It's very, very difficult to try and align square heads or other shapes of head, but with a round head, it is not a problem. The geometry is always the same, regardless of how you rotate the head. So there's clear advantages then of using round heads over other shapes of head. There must be good concentricity between the rebar and the head itself, because again, one of the fundamental requirements is that the head load is distributed evenly, or the bearing load is evenly distributed on the head. So here, if you don't have good concentricity, you need to effectively assume that you have a smaller effective bearing area of your head. And if you have a smaller effective bearing area, of course, the head is less efficient. It means you need a greater spacing requirement, and potentially you need a greater bond length requirement for your rebar. So there should be good concentricity between the rebar and the head diameter, or the head itself, sorry. And the head should be not only flat, have a flat bearing area, but it should be perpendicular to the rebar, as I said before. If it's not, of course, you get a component of force acting transversely. Whoops. So what other guidance is there? What other support can Dextra offer? Well, back in 2013, there was an interesting article that was written in and published in the Structural Engineer in the UK. In fact, Dextra commissioned this article to be written and published. And this article looks at the design, or how to design with headed bars, and it compares different requirements of Eurocode, ACI 318, as well as the FIB model code. But what it isn't is a step-by-step guide. It doesn't give you step-by-step information. And really that is why we approached Arup, the consultant engineers, to write this design guide. And now, based on this Arup design guide, which works on the fundamental principles of Eurocode 2, we now have electronic tools. So for products like our Bartec headed bar system, we have an electronic tool so that you can use either a small or large heads and input the relevant parameters and then set the design requirements from that. And these tools are available from our website to download. And we also have an electronic tool for ACI 318 for both imperial and metric units. So this is just some screenshots from the electronic tool that we have. For the particular product, you can select either one of our small heads or large heads. You select the rebar diameter from a drop-down menu, input the strength of rebar, it's grade 500, the aggregate size, and you can change your partial factors of safety. So here we have the default factors in Eurocode 2 and the default coefficients. You then need to press the calculation button. It imports the relevant data about the size of the head, and it starts to run through the calculation. So the first table that you see effectively checks to see if the size of the head is enough so that the full load can be taken via the head alone. So at the bottom here, shown in green, it's really showing that for this particular size of head, which is in fact one of our small heads, you need to use a C50-60 strength of concrete or stronger in order to take the full load via the head, as shown in green. Whereas for the weaker sizes, you need to take the load via a combination of head bearing and rebar bond. We then get a table, first of all, that deals just with the stronger grades of concrete. So working from left to right, we have the concrete grade, we have the cylinder strength, we have the design rebar stress. Sorry, the concrete design strength and the design rebar stress at the anchorage. So here we were assuming that it is grade 500 rebar, 500 divided by the partial factor of safety, 1.15 is 434.8. We then have a non-dimensional parameter, which we call XRD, which varies between 1 and 3.5, depending on really what kind of capacity the head is taking. So if it is taking the absolute working to its full capacity and taking full load, the value of XRD is 3. And then we have the spacing requirements. So the minimum edge distance, AB, minimum center to center distance, CB, and the absolute minimum dimensions to ensure that you can place and compact your concrete. And then we have the confinement, transverse confinement force, and the amount or cross-sectional area of transverse confinement reinforcement. And we configured that so that, or it assumes that you're using the same grade of reinforcement as you are for the headed bar itself. And then lastly, we have a table which gives information about the weaker grades of concrete. So here it gives exactly the same information or type of information about the load under the head, but then we also get a bond length contribution. So here again, you can see that we have the stress really taken by the head, by bearing, and the stress taken by bond. And if you, the two together equals the design compressive, sorry, it equals the design strength of the concrete, of the rebar, 334.8 MPa. And then the bond length of the rebar itself is then just calculated from the provisions of Eurocode 2. So the very last slide is just to say that we have all of our components, all of our headed bars, as well as our coupler systems in electronic format, Tekla, Revit, AutoCAD, and we also have YouTube demonstrations to show how those work. So this ends the webinar presentation. So I'd like to thank everybody for joining today and for listening. And of course, I'll now hand back to the panel, where there's an opportunity, I hope, now to discuss maybe things further and to answer questions.
Right.
Thank you very much indeed.
Yeah, thank you, Mr. Goodman. I think it was a very crisp and concise presentation with all nice information and various resources where we can look for additional details. So thank you for that. Now let me open the floor for comments and clarifications from the panel first, then followed by the participants. So let me start with our panel members. We have, I think, our number of our executive members also, they have joined. So I welcome our engineer Atul Bobe, Bhargav Jog, and Professor Jyoti Busari, and engineer Ravindra Kumar Goel, and engineer VN Hegde. And so let me start with our president, IAB president. I'm not sure. Engineer Vinay Gupta sir is there. Yes, sir. I think you can start the discussion. Yeah.
Certainly. Mr. Goodman, this is really very informative. And honestly speaking, idea of this kind of a stuff, that is headed bar, came to us only about a week ago when we heard your other presentation, from your company. And it sounds so simple, but I'm sure it is not as simple as it sounds, because whatever we provide on a small concentrated area into the concrete must withstand. The headed bar must remain intact with the rebar with this threading or whatever we do, and threading has to have the strength. And we have to also worry about the fact that the concrete there is perfect. So there's so small an area that's carrying the mechanical, not bond, but mechanical bearing onto the concrete. And therefore richer concrete will certainly have a larger. But let me tell you something that, of course, we all know about it. In the case of brackets or corbels, we do provide cross rods because the corbels normally have large diameter bars. And corbels do not have enough space for the rebar to continue very much further for the anchorage. So at the end of the straight bar at the top of the corbel, many times we do provide a cross bar of the same diameter. Sometimes we weld it. Sometimes we have the main bar wrapping around the crossbar. and that is supposed to give us the mechanical bearing or strength through the bearing, through the concrete. So this is something of that sort, but it's coming into practice. I'm glad. Only I wanted to know, Arnold, whether I missed that part of it or not. What are the kinds of tests that we should carry out to make sure, like in the case of couplers, we do have tests that we carry out. Here,
Yes.
there must be some tests that you may like to suggest, but I
Yes,
hope all the participants liked the presentation as like me. Thank you.
Yes, indeed, there are indeed tests. So you're absolutely right about your comments. You know, as I see it, there's two issues. There's the strength and robustness of the product itself, and that product you can test in air, and I'll come back to that, to ensure that the strength and robustness is sufficient and its performance is sufficient. And then the second issue is, once you put it in concrete, what is happening to the concrete underneath, as you quite rightly said. And that was really the focus of the presentation, is what is happening to the concrete. And the concrete can take so much load, so it becomes overstressed, but there's a limit to how much load it can take. And thereafter, you need to take a rebar bond into consideration. But in terms of tests, so it can vary from country to country a little bit. So in the UK, we do tension tests. So what the tension test consists of is the head head is tested in air, but it has to sit on a bearing plate, of course. But the bearing plate has an aperture, has a hole in it, about 0.6 times the diameter of the head itself. And it's thought through research and analysis that this simulates the kind of bending moment that it would see if it was in concrete. So it's not just pulled directly on to a steel surface, but it's pulled over an aperture. So it creates a bending within that head. So there's a pull test. So it's pulled to destruction. Now, with our Bartek system, as I said, Bartek headed bar system, which we manufacture the Bartek system and have that technology in it, it produces a full strength system. That is, when it's tested to destruction in this manner, it is the rebar that fails if it's a grade 500 rebar away from the influence of the head. Typically, there's also a type of robustness test too. So this is a similar test, but it's tested on a inclination. So that inclination is often about 5 degrees. So the head is pulled against a 5-degree wedge to ensure that, you know, if it were to be unequally loaded, it is robust enough again to take those loads. So they're typically the two tests that are performed. There are additional tests. So in the ISO standard, for example, for headed bars, and we've tested some of our products, we have independent tests for some of our products to the ISO standard. It gives different performance categories. So for example, there is a seismic performance category where the load is cycled from very high load in the rebar's plastic zone to very low load, and it's cycled about 20 times or so. And there is also a fatigue category in ISO requirement, where obviously it's cycled many thousands of times over a stress range. So effectively to make it suitable for highway bridges and other structures subject to fatigue.
Yeah, thank you so much.
Thank you.
All right, yeah, thank you. Let me move on to Dr. Harshavardhan Subbarao. Sir, you can.
Thanks. Thanks, Richard. That was an excellent presentation. It was quite informative, and there is definitely a need to get this into our codes in India. I'm not sure that we have sufficient guidance at the moment as things stands, either in the 456 code or in fact in the National Building Code, or for that matter in the railway codes or the bridge codes of India, which we have. I don't think we have sufficient guidance and even knowledge about this. This is not taught in any college. The idea of the failure mechanism is fundamentally different. I mean, you have a cone of fracture or a circular fracture. The failure mode is the basic issue is understanding the failure mode and deriving based upon the failure mode, of course, we're getting the kind of resistance that we are developing in bond and along with the bearing. So, and the play between both those based upon the material and workmanship of both the products, the concrete as well as the steel product, the headed bar. This is important to understand that the quality of concrete, as Vinay also said, invariably the shortfalls in the quality and grade of concrete, you might say it's M40, but the workmanship and compaction near the bar may not be up to the mark. So then, of course, there is a level, a level of, I would say, uncertainty that creeps in. Now, how do we deal with that in the design? I mean, do we load a partial safety factor to account for this more and above everything else? Or is it just taken as, it's deemed to satisfy all requirements? This is one issue. The other issue, of course, Richard, is the tolerances, both of the rebar in its manufacture and its placing. I'm not talking about your Dextra rebar. I'm talking about, in general, a headed rebar. The tolerances of manufacture and therefore the reduction values in strength or bond and so on, and also the concrete I already spoke about. So these are things that we will have to try and understand more clearly from you. And I invite you to join us in trying to come up with some guidance for our codes, because there's clearly advantages in using a headed bar. There's no doubt about it. Being used for quite some time elsewhere other than here. So I would like to also to ask you and other panelists where this is being used in a large way in India and how it is in built performance, how it is performing in service, and what is the use elsewhere in the world, what is the built performance of the product when used. These are the questions and ideas I would like to share.
Yeah, maybe I can, I'm afraid I can't answer all those things directly, but I'd like to just talk around them a little bit from my own experience. So in terms of using the products around the world, so perhaps the largest project that we're supplying to at the moment is actually in the UK, where I am based, and it is for Hinkley Point C nuclear power plant. So here we are using millions of headed bars, which we are supplying. And these have been used for the main raft for the nuclear reactor. They've been used as cross-wall shear ties, used as transverse shear reinforcement, and a number of different applications. Primarily, they're being used on this project because of the ease of use. Because there's certain situations where it would be very, very difficult to have a bent length anchorage at both ends. It would just take so much time to construct it to do that. I think as you saw in one of the photographs there of the very, very thick raft. Yeah. And also, of course, because of congestion issues. So yes, they are being used around the world. And a lot in other countries, Japan, Australia, Northern America. In terms of designing to India, in India and to the Indian codes of practice, what I can say, I mean, I've looked through some of the codes of practice. So I've looked through IS 456. And the relevant device. And as I said in the presentation, of developing the strength of the bar without damage to the concrete may be used as an anchorage with the approval of the engineer in charge. Yeah. So, okay, there's a clause in there which says it can be used, but of course it doesn't say how they can be used. But thinking about it a little more, I mean, certainly one of the things to do would be to maybe look at the provisions of Eurocode as implemented by the Arab Guide and the fundamental principles of how it works and how you get this stressed area, but at the same time use the parameters for factors of safety for your concrete, for your reinforcement, and also your bond provisions in the Indian standards instead of those in Eurocode. So that kind of approach could be taken. So using the same principles, but you're substituting perhaps the parameters from Indian codes of practice to establish your, your rebar bond, to establish your concrete strength and all your partial factors of safety. But you're right, all these things need to be looked at in detail and gone through. And certainly we'd be happy to be part of that.
Thanks. Thanks.
Thank you, Dr. Shodhan. And now let me move on to Engineer Alok Bhowmik. Sir, you can give your comments. And
yeah, thank you. Am I audible?
Yes.
Yes.
Yeah, okay. Thank you. First of all, I would like to, profusely thank Mr. Richard Goodman for such an excellent presentation. I mean, it was mind-boggling on a subject which was little known to me, but the way he presented, giving, a comparison of various codal provisions and also the design guide which was got done, and the way this whole subject was presented is absolutely commendable. And the key takeaway from me is, this is the way when you launch a new product, this is the way one needs to market. It's a lot of takeaway for many of us. Particularly, there are many such products which are in the market, but I think if that product is presented in this lucid manner, as to which makes the designer, somebody who wants to actually apply it, he has all these avenues by which the product manufacturer facilitates. Now, having said this, I see a lot of application. Of course, in India, I have never heard of never used myself this headed rebars, but I see a huge application, particularly in congested reinforcement areas, like, for example, in pile caps, for example, in corbels. We can also use it in beam column junctions, and anywhere where the reinforcement condition is there. By the way, we have been using it in bearings, in pin bearings and in pot bearings. We use these headed studs. Practically, it does the same thing. Not a rebar header, but the stud heads, and that has a similar function. But that is a part of the bearing system which we have been using it. Now, I have few questions or queries to Mr. Richard Goodman. One is that I just want to know, when you have this product, let's say one wants to use it. Now, who takes the responsibility for what? I mean, the bar is, the header will be supplied by by Dextra, and who will supply the rebar? Who will do the connection? Is the designer takes the responsibility, or is the product vendor who takes the responsibility for correct functioning of that particular connection? A. B. What are the field acceptance criteria for this kind of, at the field, when you get the product, how the the contractor or the client would accept? What is the acceptance criteria? These are areas which I think, if you can slightly elaborate, it will be better. On the whole, it was an excellent presentation, and I don't know whether these guides which you mentioned, are they in public domain or they are not in public domain? I would certainly like to go through those guides if it is in public domain. Thank you.
Yes, certainly the guide which has been written by Arup, we commissioned Arup to write, is in the public domain. It is available to download from our website, or we can certainly forward that to you. So that is in the public domain. But yes, very, very good comments and questions about the suitability of products and who takes design responsibility. The processing of the end of the bar itself. So with our Bartek system, which we sell in India, the end of the bar gets cold forged, so it's made larger before threading. That operation is completely done with machinery which is designed and manufactured by Dextra. So we take responsibility for that and the connection and the strength of the connection with the head, and we sell the head. So even if, as is sometimes the case, the machinery is maybe on site or with a rebar fabricator that cuts and bends the bar, we service that machine, we look after it, we give instructions on how it's got to use. So we take responsibility for the product. In most countries, then there's some kind of requirement or regime to test that product, as I said before. So it can be tested at laboratories in air. And again, we don't have any problem in sharing the test reports and the information that we have for all of our products, because indeed, we have an in-house test laboratory ourselves, which is run independently from the rest of the company. And so we are able to test these products all the time and continuously test them. So in terms of the product, we take, and its performance, we take that responsibility. In terms of what's happening to the concrete, of course, well, the guide is written by Arup, and effectively they have taken responsibility. They put it in writing, and there's no limitation on putting that into the public domain. They're happy for that to be put into the public domain. That was a discussion we had with them early on, and happy for it to be used. And within the guide, it does say that it's designed for use as a non-contradictory and complementary supplement to Eurocode 2. So they've, if you like, taken responsibility for what is written in the guide. We've then taken that information and put it into an electronic format. But it can, if necessarily, be cross-checked by engineers.
Just a point, Richard, you probably are aware that the IRC 112 code, that's the Indian Roads Congress, which deals with bridges. The IRC 112 code is largely derived and based on the Eurocode.
Okay.
So it's largely, I would say, most of it is directly taken from the Eurocode. So there would be an easy edge for us to use this guide and to adapt that guide and utilize this very quickly, actually.
Okay, yeah.
Okay.
And the other point Alok makes, Richard, is about suitability testing. The point really is about suitability testing. So what are the parameters that you have to have, and what are the suitability tests that are they defined suitability tests that have to be done?
Yeah, well, in a lot of countries, they have there's some kind of product certification scheme. So in the UK, for example, we have a product certification scheme. So for headed bars, the product is certified. So it's tested to achieve certain parameters. And then they say, yes, it's achieved those parameters and it's certified. And then thereafter, it is also routinely tested periodically on a 6-month basis, and they make sure they run through all the diameters. And they also monitor the company. If a different company is actually attaching the head or processing the rebar, they monitor that process also. So they make sure samples are produced by this third party and that they're tested to make sure the whole process is correct. And there is a defined then testing requirement whereby the head is tested or loaded in tension to destruction. And often there's a robustness test too. Now, in terms of the strength requirement, that changes from country to country, as do the requirements for couplers, in fact. So some requirements say that the failure load must be above just the minimum ultimate failure load of the rebar, but doesn't need to be the actual failure load. And others have other countries have a more stringent requirement. In terms of our Bartec product, that is a full strength head. So ultimately the failure will be in the rebar that's attached to and be away from the influence of the head and the connection. But we would be very happy to suggest testing requirements and also forward any testing certificates and information that we have conducted ourselves with the product.
All right, yeah, thank you. Now I'll move on to the next panelist, Engineer Umesh Rajashekar. Sir, give your comments.
Yeah, thank you, Richard, for your excellent presentation. I have a couple of questions. especially from the design point of view. See, Eurocode for the fatigue design, there are different resisting stress range for mechanical couplers, and they are quite less. For example, for the reinforcement, that stress range, if it is a 165 MPa, for the coupler, they have reduced to 35. So can you categorize this head in the same category as a mechanical coupler? So in that case, the stress range resisting would be substantially less. That is the one point. You would like to answer, and then I will ask the.
Yeah, if I could. Yes. So with our Bartec product, for example, so we have a Bartec rebar coupler system, and we have the Bartec headed bar system, and it uses the same technology. And so effectively, you would get the same level of performance from the Bartec coupler system as you would with a headed bar system. So we would expect the fatigue performance to be very similar between them. So yes, the fatigue performance would be less than the rebar itself, and we would expect that, and be similar to rebar couplers.
In this your coupler, there is a mandatory requirement for a cyclic load test. So we test for some number of cycles, maybe a millions. So similar guidelines are there for this headed bars, and what amount of number of cycles this American or other countries they specify?
The only standard that I know of, without investigating a little further, the only standard I know of is the ISO standard for headed bars, which, as I said, there's different categories, and there is a category F for fatigue. But I'm not sure offhand, I'm just seeing if I have the information here, on what it says with regards to load cycles and the stress range. But that is the only product standard I know of for headed bars that gives a fatigue test, and that is ISO 15698.
So this is with respect to the reinforcement and headed bars. But since we are getting a very concentrated compressive low stresses in the concrete behind this headed bars, again, we may have to check a concrete also for a fatigue verification. In the Indian code, how we have avoided, we have kept the maximum permissible stress in the rare combination equal to 48% of a FCK, and that's how we have avoided the fatigue check in the concrete. But if this particular zone is subjected to the very high compressive stresses, then may we have to carry out the fatigue check for a concrete also in case of a bridges. So that will be additional calculations we have to do depending on the how much stresses they are there behind this headed bar. Just a comment. Okay. Then please.
Yeah, one thing I can also sort of elaborate on the requirement for testing in ISO 15698 is that, let me just have a look here. I think I'm right in saying that the fatigue test requirement, let me just double check this. Yes, so this is there's a specific fatigue test requirement, and actually it says that if it is a large head, so if the head area is 9 times the bearing area of the bar, that fatigue test can be performed in air. But if it is a smaller than 9A head, it says the fatigue test has to be done actually in concrete.
Okay.
But,
so have you done similar such test in actually? Have you done this test of the smaller diameter in a concrete?
We have done some tests. We haven't actually. We have tested some headed bars in concrete with our large head. So we've tested for the seismic category in ISO 15698. So we've tested for the seismic category, which is cyclic loading under sort of low cycle plastic elastic loading.
Okay. There are a couple of questions regarding the detailing. See, some of your photographs were showing for a shear reinforcement, you have just provided the headed bar, and we provide a link around the main bar with a bend of about a 135 degree. So in a seismic ductility design, generally we prefer such detailing to avoid the opening of this shear reinforcement. Correct. So in case of this headed bar, how it will perform? Are there any full-scale testing has been done in a laboratory to see the full capacity in the plastic hinge region is getting developed?
Yeah, there are, while I don't have details at the moment here, but there are quite a lot of testing reports and papers that have been written about headed bars, both for joints, so beam column connections, for other types of connections, and for shear reinforcement also, and the use of headed reinforcement in shear reinforcement. We actually have quite a few of those reports that are on the market, probably the vast majority of them. And in fact, there are tests that are still ongoing in the United States with headed bars, particularly with very large rebar diameter and with different parameters. But there is quite a lot of technical reports out there about headed bars and their use under different conditions.
I just add to what Raj, just to carry that point, and then you ask the question again. The point is about confinement, because when it is closed, when the stirrup is closed, or it's fully closed, and you have your 135 degree type bend, then you're confining the concrete and allowing it to get plastic, based upon the spacing, of course, but you create a region of high confinement to allow plasticity to develop. When it's U-shaped and with corners, it's a U-shape basically. How do you ensure the confinement and the development of the plastic hinge? That is the fundamental one. And the other also about fatigue, which Raj asked, I want to just add to that. Fatigue will be not a one-time sort of situation. It will vary based upon the grade of concrete because of the failure mode, right? It will vary based upon the underlying concrete below the headed bar, and also on the headed bar itself, its diameter and the diameter ratio, if you like, the size of the bar to the size of the head, the outstand, if you like. It will vary completely with the outstand. So you can't have one stress range, or you cannot have one defined parameter, I would think. It would be a varying parameter in terms of these varying values or varying stress range based on these parameters, Raj.
That is given in a Eurocode, so that can be easily calculated. Richard, I have just one clarification. Is any international code like American, ASTRO, or Japanese code have put any restriction on this headed bars in any situation like earthquake or earthquake-prone zones? Or so are there any restrictions put by any international code on any situation?
Certainly in terms of earthquakes, so ACI 318 for headed bars, as I explained, it allows the load. It allows for a small head and the load to be taken by the head and rebar bond or development length. And in the section of ACI 318 that deals with earthquakes and earthquake design, it says that you can, explicitly says that you can use headed bars, but it says effectively to take the design load as 125% of the load that you would otherwise be taking, or it says to take it as 125% FY. Effectively, that's what it says in terms of designing with heads, but they use exactly the same information and parameters. But there's nothing in Eurocode specifically about using headed bars, particularly in seismic zones.
Fine, that's all. Thank you, Richard.
Thank you.
Yeah. Thank you. Now let me open it with the other panel members. Engineer Ravindra Kumar Goel sir. You're muted, sir. You can unmute.
Thank you, Dr. Surya Prakash. Let me congratulate Mr. Richard Goodman for a wonderful presentation. It is a new concept introduced to me for the first time, and I find its efficacy. It has got a lot of scope for application in India, I would say. I have got only one doubt, how it is going to be used when the reinforcement is in compression. In tension reinforcement, I can find that it is very, very useful. But in compression, how it is going to be useful? This is I'm not able to understand. If you can explain.
Yes, well, in terms of compression forces in the rebar, then of course what would happen is that if you have a load on the head, there's the potential for it to normally punch out of the concrete, which is obviously a problem. So normally, to deal with compression loads, you would simply make sure that you have enough length of rebar in front of the head to act as an anchorage for the compression loads. And certainly in American codes, in ACI 318 and in Eurocode, that is exactly the same thing that you would do with a bent bar anchorage. So you would take a straight length in front of the bend of the bar for your anchorage in compression loads. So there is a small advantage in using heads in that respect, in that you can start your length closer to the edge of the concrete, your bonded length. So you could have a little bit of a smaller anchorage zone than with a bent bar anchorage.
Okay. So you mean to say the length of compression zone, the length of the anchorage zone will reduce, and to that extent, it will be helpful.
Yes, that's right. Because although if the rebar is in compression and you need to take a bonded length of rebar to resist that compression load, it is the same length with a bent bar as it is with a headed bar, but with a bent bar, you need to start, that length would start actually closer to the edge of the concrete with a headed bar.
Okay, thank you.
Without a diagram, it's maybe a little difficult to illustrate, but if it's easier, I can actually go back to my presentation because I have a slide which shows that.
No, it's okay. I got it.
Yeah,
thank you very much.
Yeah, I think the advantage is
Thank
limited,
you.
but as I said, that you can have a slight reduction in your development length. So you start from the edge. That's what I understand. Yeah. Okay.
Yes.
Let me ask from other panelists. Due to paucity of time, let me open. If you want to ask question, Professor Jyoti Dusari or Hegde sir. Yeah,
I would like to say something.
Sure.
Actually, I'm a professor, and last year itself, one of my PG student, he had conducted one experiment using this headed bar as a anchorage in beam column joint. Okay, we carried out this particular research in CSIR Roorkee. It was sponsored by BJ Shirke. This is one of the premier institute in India, CSIR at Roorkee. And we had scaled down models of beam column joint that were made. But what problem initially that we encountered was related with the concrete breakout failure itself. And specifically, I would categorize it as a side blow failure that occurred. So it was related with the anchor bar, which was placed at the extreme end of this. So we increased the cover later on, and then this problem was sorted out. So specifically, when I'm using this headed bar, I think the cover to the this thing reinforcement, it has to be increased. Is that so? I would like to you to
yes.
elaborate
I
on
mean,
this.
there are potentially various mechanisms of failure, and one of them is a side blowout failure. You're correct if you have the head too close to the side of the concrete. So with the designing and with the Arup Dextra guide there it details what the requirement would be for the amount of cover, effectively from the center of the rebar to the edge of the concrete, and also what the transverse forces are. So you need to resist those transverse forces, particularly if it's close to the side of the concrete, with confining reinforcement, and ensure that you have enough space there. But absolutely, if you're too close to the side there and you don't comply with those rules, then you can get a side blowout failure.
Yeah. So from the conventional, whatever cover we provide, when I'm using this headed bar, I have to increase my cover. That is what.
Yes, correct. Yeah, if you were to use just your conventional cover, say to the head of maybe 50 millimeters or so, it is likely to be insufficient. You're absolutely right. Yes.
Right.
Yeah.
Thank you, sir. It was
All
excellent
right.
presentation. Yeah.
Thank you very much indeed.
Yeah. Thank you, Professor Basari. Now, I think Engineer Hegde, sir.
Hegde, if you
Hegde,
have
sir.
anything to add.
Yeah, Mr. Hegde, sir, you can unmute and yeah.
Yeah, I'll be taking very.
Sure.
I know that the time is running short, so I didn't want to come in between. But I'd like to congratulate Mr. Goodman for making this presentation very interesting, because this is not the kind of presentation which can be made interesting so easily. As a Goodman, you have made this presentation very, very interesting. I have to congratulate you on that. And also you have given insight into to us where the headed bars can be used. What we have to understand, all of us here, is the headed bars are not used in a routine, regular applications. It has to be used in a special applications where the congestion of the steel is, like that problem has to be sorted out. And also, if I recall, this concept of the headed bar, if you really look at the passive anchor designs, like if you really look at the passive anchor designs, at the end of the anchor, you provide a plate that is nothing but a head. And when you pull the anchor, there's a compressive stress in the concrete, and that has to be checked. How to check that? Even our Indian codes, like that gives, but it doesn't give that, like that you will have to take this bursting tensile stress will be there. You will have to provide the reinforcement to take care of this bursting tensile stress. But it is similar to that of the pitch concrete anchor too. When you do the pitch concrete anchor, instead of we are applying the anchor force over there, there is a bursting tensile stress. You'll have to take care of that. You'll have to provide the reinforcement. The concept is there. As Mr. Alok Bhomik also explained, the similar concept is used in the bearings also. We have got a stud there and there is a head. In case of the reinforcement, reinforced concrete, where the reinforcement is used, because of the deformation or the strain in the steel, and there is a development length which is required at the end of the bar, that development length is replaced by the bearing area there, bearing of the stud over there, or the stud or the head over there. That area should be equivalent to that of the development length which you are going to get. This concept which we have used without the codal requirement, where the reinforcement congestion is quite a lot in many of the places to get the necessary development length, but we are getting the codal requirements as well as the design rule now, and it has to be used. I just want to highlight again, this is not a regular and a routine application. It is a specialized application. We'll have to see and use it. It cannot be used as a to use it as a routine as far as the specialized application. There are some complexities at the site. Say, for example, the couplers. When you are providing the couplers are made as well as the threads are made at the site itself. As Goodman has explained, normally they provide the machine at the site, and the thousands of couplers have to be prepared. The threading has to be made. Normally, that is made at the site itself. And similarly, when you're going for the headed bar, if you're going for a large voluminous use of the headed bar, I think the machines have to be provided at the site itself, and the studs or the heads as well as the like the threads has to be provided at the site itself. And also, if you have to provide the factory make you will have to get from the factory, then you will have to get the cut lengths. Thread is already made, heads is already made, and if you are using for the different types of the bar, diameter of the bar, you will have to get the different diameter of the bar. Not only that, if all the reinforcement is provided with the headed bars, say imagine a situation, there is a possibility of getting the congestion of the like the area also. It's all covered with the head at a particular location. So I think it's a special application. We'll have to see where it has to be used regularly. And this question of fatigue, which Raj Shirke used, I thought I would be asking that question. I think Raj Shirke, as a like a hardcore design engineer, he has hit on the head of the nail, saying that from the fatigue consideration, headed bars may not be so economical. In fact, not only headed bars, even the use of couplers may not be so economical. Reducing from 160 to 35, the stress range, it's a heavy premium on the quantity of the steel. I think that kind of quantity of the steel we may not be able to save in terms of the bond length or the development length. That's what I feel. So again, I repeat, it's a special application in my view, and it has to be very carefully used where the special application is required. Good one. Thank you very much. It was an excellent presentation. You made this presentation very interesting and stimulating even. Thank you very much for that.
Thank you for your comments. Thank you.
Yeah, thank you. Thank you, Hegde sir. So I have one question, I just out of curiosity, as under cyclic load and things, we develop this bursting tensile stresses. One thing is, for reducing the congestion, we are going for this headed bars. On the other hand, to reduce these bursting tensile stresses, we are again adding more reinforcement, probably in a smaller quantity. Has there been any attempt to alleviate this problem by adding some discrete fibers? Because that also would reduce bursting tension in a very significant way. I just, thought, if there is any work done in that direction.
Yeah, it would certainly increase the concrete strength. You're right. I don't know of any specific work with concrete fibers in conjunction with headed bars for the bursting reinforcement. But for sure, the principles of their use could still apply. Yeah, I agree.
Right. So thank you. I hope we can take another 5 minutes or so because some questions are there from participants as well. Because it was a fantastic discussion. A lot of points were raised. And we also have like 7 questions which are open. Before that, I request Deepika to project the next webinar. Yeah, so for the benefit of all the participants, we are going to have on the 7th of May, Friday, another interesting webinar on fiber reinforced polymer bars, rebars, as to be used as a permanent internal reinforcement. We all know that FRP is extensively used for structural strengthening, but here we are talking about use of these bars as internal reinforcement from durability point of view. Again, we have fantastic speaker from Dextra again, Pierre Hoffman. So the participants are requested to register and attend. Right. So let me move on to the questions from the participants.
Yeah, so Deepika, you can unshare this and bring it back to the normal screen we had earlier about all the panelists on the screen.
Yeah, thank you. Yeah. So the question from Dr. S.K. Dhawan, he is raising corrosion prevention of these coupler system in marine environment. And again, what is the saving of rebar in road and railway bridges? And what are your comments on that? Because possibly because of this extra threaded thing that it may lead to stress corrosion. So there are some concerns. That's what he's asking.
Yes. So the first question about corrosion prevention of rebar coupler systems in marine environments. So if it is a rebar coupler system or if it's a headed bar, if it is embedded in concrete, the mechanisms of corrosion will be the same as those with that which apply to the reinforcement. So traditionally with reinforcement, you allow for sufficient cover to prevent ingress of chlorides, for example, into the concrete, and provided there is sufficient cover and the quality of concrete is sufficient, then it should prevent corrosion within the relevant time period. However, I'm very aware that there's a lot of data to indicate that in the most extreme environments, particularly the most extreme chloride environments, sometimes existing provisions within codes of practice aren't sufficient to prevent rebar corrosion. That seems to be where the data is. But I see it as exactly the same situation with rebar couplers and headed bars, in that yes, you need cover. In extreme environments, you may need additional corrosion measures. And it may be that one solution that you could adopt is to adopt stainless steel reinforcement and stainless steel couplers or headed bars just maybe in the near surface layer of your reinforcement. And of course, there are other options for to help prevent chloride ingress and corrosion of reinforcement.
Yeah, the second question was, I mean, just a rough estimate, how much would be the savings in rebar quantities?
Yeah, that's, I'm afraid, a question which I can't
I know. It's a difficult one, yeah.
We've thought about it, and we've tried to think about studies we could produce, or in collaboration with contractors, but we've never managed to get sufficient information in order to produce any realistic or meaningful data in terms of savings, or in terms of savings for time or amount of steel that's been used. So I'm sorry, but I'm really unable to answer that question directly.
No, I think just look at the technical merits and demerits. That's it. Technical. That's important.
Right. Okay, and a couple of them have asked, questions. Is there any big projects in India that you can quote, or examples in India where it has been used?
As far as I know, we have not supplied any headed bars into the Indian market to date.
I think Mr. Job mentioned there is a project Kakinada or something like that.
Kakrabara Atomic. I think
yes,
Lehra is
power plant.
Participant. He may throw some light.
Right. So, let me finish this question. Okay. Probably I had asked him to raise the hand, then probably he can comment on it. So, and so that we have answered. I think, I think most of the other questions, I think we have already answered. Now let me go to the participants, those who have raised hand, maybe a couple of them. Let me start with Mr. Sachin Hatali. Can you unmute and ask the question?
Deepika, can the participants be unmuted, or?
I can give them access.
Okay.
Yeah, I think
Mr. Sachin Hatali, right?
Yes.
Okay. I have given him the access to talk.
So, Mr. Hatali, please unmute now and then speak.
Okay, probably he may not be around. So let me move on to next. I think Mr. A.K. Laharia, he's a gentleman. I think you may be able to give more details on that nuclear power plant where these headed bars have been used. So Deepika, can you unmute Mr. A.K. Laharia? Sir, you can unmute and give your comments about where you have used this headed bars. It looks like, I think,
I have requested them to unmute themselves, but I am getting no response.
Okay.
Let's go to the next one.
Right. Then I think I don't have the name. It is gsharan17@gmail.com.
Sharan sir.
Okay.
Oh, our Mr. Sharan.
Yes, our Sharan sir.
So you can unmute yourself and you can give your comments. Mr. Sharan?
Mr. Sharan? Yes.
Yeah, are you able to hear me?
Yes.
We can hear you, sir. Yeah.
Good evening. It's a very nice presentations, and I was very keenly observing because when I take it to BIS, where I am heading one of the committee, concrete reinforcement, and with the help of Dextra, a few years back, we have published one IS code 16172 reinforcement coupler. So I just want to understand, I've seen the concern, all those who are present here. So I will very much like, with the help of Dextra, where Sunil Desai helped us in last time, whether that IS 16172 can be extended to include this headed bar, or we can go for a separate IS committee. So when I was hearing very carefully Mr. Subbarao, he said that there is no Indian standard. Then I came to this conclusion that our committee, which is very actively, and Mr. Hegde also is here, who is a member of our committee. So with the help of all those and concern expressed, which are very clearly and vividly try to understand. So when we discuss this issue in our committee of CED 54 of BIS, so I'm very hopeful that we can have an Indian standard in a very soon. And as rightly said by, we have already coupled a reinforcement standard. So I really need help from the Dextra with the help of Mr. Goodman, and he can be asked to make a presentation in our committee in due course of time. Of course, this is COVID days are very bad, but our committee is still very active otherwise. So if they can write us with the Dextra that this can be taken, and if your committee can also forward us to BIS, the Civil Engineering Division, or to me as a chairman of CED 54, it will great help not for professional engineer but the country and the manufacturer who wants to indulge in this type of activities, because this coupler has come in a very big way. And of course, any new product has plus minus. So we are in nothing is cast in stone. So we would definitely like to improve it. And as it was rightly said by Mr. Hegde, that it can be sparingly used. Okay, but the designer and the user must be told these things are available. It is up to us whether we use or not. So that is what I have to say. And it is really, I definitely want to thank, because today my presence with all of you was helping me, and I have become much more greedy as the chairman of my committee, that I will be adding one new feather to my BIS committee with the new product, and with the manufacturer take a call in due course of time. That is what I have to say. And I need really help from all those who are present here and panelists here, who really, and then till today there may not be headed bar, but tomorrow sparing we can use some of the product, and definitely this will have advantage, although it was told how much saving. So let us not bother present for the saving. Let us bother for new material and new technology, which can definitely help. As regard design aspect, I'm not touching, because IS 456 is there, they will take care. But for the product to be manufactured in the market with IS code for licensing, our committee will definitely play a very important role. That is what I have
Thank
to
you,
say.
Sharan sir. So, Mr. Desai, why don't you please write a letter, official letter to Mr. Sharan, whose email ID is right here in front, and copy to Mr. Sanjay Pant of BIS. That would be of use, and then it can go forward.
All right. So thank you. I think yeah, we are running really little late. So already we passed 10 more minutes. So I think due to the
I'm not asking my question for that reason.
So thank you. I think I am sure Mr. Goodman would have a lot of other commitments as well, so we should honor that. So, and I would like to thank all the panelists and the participants. I'm sure you can write to Mr. Goodman, and also I request Mr. Goodman to share, if possible, the PDF copy of the presentation and the Arab Dextra guide that you're talking about. Then we can share it to the participants. So
certainly,
yeah.
Yes, certainly do that.
Right. All right. So thank you. I think now I will leave it to Mrs. Swapnil Joshi to take it forward. Thank you. I really profusely thank you to all
unmute yourself. Yeah.
So thank you, Sir Prakash. Now I will propose a vote of formal vote of thanks. Since Gopal is not there, that is my duty. So it won't be a shairi and all. It will be a regular vote of thanks. So I'll go ahead with it. So first of all, first and foremost, Mr. Goodman, thank you very much for your amazing presentation. Very, very informative on a special topic. Thank you very much for taking out of a time from a busy schedule for today's lecture series. Thanks a lot. Thank you very much. I would like to thank today's sponsor Dextra for their valuable support and participation, and hope to get your support throughout the journey of this special lecture series in dissemination of knowledge, which you have been doing for long now. Thank you very much. I would like to thank today's moderator, Dr. Surya Prakash, for his valuable comments and his time. Thank you very much. I would like to thank today's esteemed panelists, Dr. Harshvardhan Subbarao. Thank you, sir. Dr. Rajesh Shirke Saab, thank you very much. Engineer Alok Bhaumik, thank you very much, sir, for your valuable inputs towards today's presentations. Thanks a lot. I would also like to thank today's participants, without whom this wouldn't have been a great success. So thank you very much for keeping a faith in IIB and continuing towards this lecture series. I would like to thank all senior members of IIB and the executive committee members for their participation in all the lecture series and for today's event as well. Thank you very much. Special thanks to our Director General. He could not, due to some reason, he could not attend today's session. Engineer DJ Dute. Our president, who is both of them are a great support to us, to keep on going and exploring new things. President Engineer Vinay Gupta ji, thank you very much. Secretary Gopal Rai, he could not attend today's session. V. Agarwal also has been requested for leave of absence today. Deepika Singh for a great coordination support, and Josefa, who is taking care of our IT support for all the sessions. So with this, I think I would like to thank each and everybody who has made this a success, and I officially would like to declare that today's session is closed.
Thank you so much, and please do join in on the 7th May, next Friday.
Yes, please do that. Thank you very much.
Thank you. Thank you.
Thank you, gentlemen.
Thank you, ladies.
Thank you.
Thank you, Mr. Richard Goodman.
Thank you, everyone.